So far, we have covered linear programming. Linear programming is the most frequent type of optimization problems solved in practice. Nowadays, we have very good software which is able to solve linear programming problems if we have millions of variables and hundreds of thousands of constraints. So we are talking about really huge optimization problems which frequently occur when we want to allocate transportation, for instance, to individual transportation channels, and to many other economic and production optimization problems, as we have seen both in the lectures as well as in the exercises. If you are brave enough, you can even solve linear programming in Excel. Excel provides a linear programming solver where you define the objective function and constraints using cells, so each cell will contain one multiplier of the corresponding optimization variables. And then you can use the built-in linear programming solver to actually solve the problems. It's not the most efficient solver in the world, but it works. Today we will cover the second large class of optimization problems, which is called quadratic programming. It is very similar to linear programming. So we still have linear constraints, both equality and inequality constraints. However, we will have a quadratic objective function. And these kind of problems, they frequently occur in practice when we want to minimize energy of certain signal or physical quantity, because we know that the energy is proportional to the square of the value of the signal. What we will do today is we will go through two main parts. The first one will be theoretical. We will look at how these kind of problems can be formulated and solved. And then in the second part of the lecture, we will cover applications of quadratic programming. In particular, we will talk about two classes of problems. The first one is extended fitting. So essentially, we will look at least squares fits. And you all know that least squares already has a quadratic objective function, so it fits nicely into this framework. However, we will also consider the case where we want to enforce constraints on the fitting function. And we will talk about something which is really interesting, and it's called sparse fitting. Sparse meaning we would like to find the fitting function which is simple. And the second class of applications that we will apply quadratic programming to will be in the field of separation. You probably remember one of those motivating examples that I have shown previously, like when we have two types of production units in our factory, and we would like to separate them by a wall. Okay? So we will talk about the pure linear separation, where the wall has to be a straight line. We will talk about something which is called robust separation, and also about so-called approximate separation. And all these problems can be easily formulated as either linear or quadratic programming problems. So let us start with the theoretical formulation of quadratic programming. In quadratic programming, often we abbreviate quadratic programming by QP. So when you will hear somebody saying QP, he means quadratic programming, and when somebody says LP, that means linear programming. So in a QP, we have a quadratic objective function where x are the optimization variables. We know that we can have many optimization variables, so they are all aggregated in this vector x. And we have an objective function which consists of a quadratic term in x. We have a linear term, and we have a constant. And we might also have constraints. We might have inequality constraints or equality constraints. What is important here is that even though the cost function is quadratic, the constraints must be linear. Okay? So this is what makes some optimization problem a quadratic programming. Quadratic only applies to the cost function, but the constraints must be linear. Now, by must be, we mean that if we have a problem like this, we can solve it rather easily, provided the cost function is convex. And the cost function is convex when this P matrix here is a symmetric matrix, meaning transpose of the matrix is equal to P itself, and P is a positive definite matrix. Positive definite means all eigenvalues are strictly positive. Now, the consequence of assuming that the P matrix is like this is that it is invertible. And we will see in a second how invertibility of the P matrix helps us to solve the problems rather easily. If P is not a positive definite matrix, actually it can be a not positive definite matrix in two situations. The first one is it's a positive semi-definite matrix, meaning at least one eigenvalue is 0. That's still kind of an easy problem. But it can also be that this P matrix is indefinite, meaning its eigenvalues are both positive as well as negative. Now, a negative eigenvalue would essentially mean that we are maximizing a convex function. And we know that maximizing a convex function is a difficult problem. Just imagine like a square function and minimize minus x squared. Okay? So essentially the P here is this minus 1. That's our P. Okay? And it's a negative definite matrix. And maximizing this function, well, depending on the constraints, either the optimum is here or there. But the point is there is a choice. And once there is a choice, it's no longer a simple optimization problem. So here we are back to the argument why convex optimization problems are easy to solve. Because once we find one optimum, we know it's the global optimum and we don't need to search any further. Okay? So essentially, these two assumptions mean that this objective function here is convex. We know that linear constraints are convex as well. So in short, we have a convex optimization problem, which, if it has an optimum, it is a global optimum. And this property will help us a lot to devise an efficient algorithm to solve optimization problems of this form here. Now, what we are saying here is that it could also be that P is a positive semi-definite matrix. A positive semi-definite matrix, if we have just a scalar optimization variable, would mean that P is equal to 0. Okay? However, if P is equal to 0, what kind of problem do we obtain? Because it's always about choosing the right algorithm for a particular problem. So far, we have seen linear programming. Linear programming is the simplest possible optimization problem. Quadratic programming is something more difficult than linear programming. So if somebody gives you a problem like this and tells you that the P matrix is 0, which lecture you will essentially look for from this class? Linear programming, because it's reduces to a linear program, okay? And you would be surprised how many people are just blindly applying the algorithm without realizing that the problem in fact is a simpler problem for which a more efficient algorithm exists. So those algorithms for linear programming are more efficient, meaning in the same amount of time we can solve an optimization problem which is more complex in the terms of number of variables and the number of constraints. As I said, for linear programming, we can, not easily, but it can be done to solve an optimization problem with millions of variables. For quadratic programming, in the same amount of time, we can only solve a problem which has roughly 100,000 of optimization variables. So imagine that you have a problem with million variables with P matrix equal to 0. If you apply the methods of this lecture, you will probably not be able to solve the problem because you would be doing QP-based method applying it to linear programming. However, if you would use the simplex method, you could solve the problem despite it being much larger. So the question is totally obvious. What will happen if p is equal to 0? What is not obvious is that you have to realize this and use the corresponding solver for that kind of problem, not for quadratic programming. Okay? And actually, let us now look at how do we solve these problems. And let us consider 3 possible scenarios. The first one is the simplest one. Let us assume there are no constraints. Now try to reach several lectures back. How do we find the optimal solution to an unconstrained quadratic program, assuming that the P matrix here is positive definite, meaning it's invertible? How do we solve this problem? How do we solve any optimization problem? Sure. So we just need to set the gradient of the objective function equal to 0, and we need to consider the gradient because x is a vector. Okay. So what is the gradient of the objective function? Let's call the objective function j as a function of x. What's the gradient of that? What's the derivative of x transposed px with respect to x? That's 2px, and we have 1/2 in front. Actually, the reason why there is this 1/2 is exactly because of to get rid of that constant multiplier in front of the derivative. So we have px plus q, and we know that at the optimum this has to be equal to 0, right? So assuming that p is invertible, x is just p inverse minus p inverse times q. Okay? And yet again, one instance where quadratic programming occurs very frequently are optimal control problems. You are familiar with the linear quadratic regulator, which is kind of a particular form of quadratic programming. And actually what we see here is that we have a minus in front of the optimal solution. And this explains why negative feedback is the optimal feedback. Okay? And you know feedback theory, and we consider negative feedback, and the answer is actually nature. Nature says that negative feedback is the optimal solution. Okay? So that's the optimal solution as we can find it very easily. Okay, so these are toy problems. What is the difficult part when finding the solution? Or when somebody asks you, okay, so how large can this problem be such that I will be able to solve it? Yeah, we need to perform this matrix inversion. And we know that in general, the matrix inversion, if n is the number of optimization variables, then the matrix inversion has complexity which is in the order of n cubed. Okay, so with 1,000 variables, that's probably 1 billion, or in the order of 1 billion of operations. That's probably doable. If the number of variables is 1 million, that's not doable. Okay, so that's also the reason why quadratic programming procedures are limited to fewer optimization variables than in linear programming. In linear programming, we were not doing any matrix inversions. Okay? All we were doing is we were just performing elementary row operations, and that's much, much easier even if you have a large number of optimization variables. Here we have to perform matrix inversion, and that's actually the bottleneck of all quadratic programming algorithms. So this was the unconstrained case. Let's make it a little bit more difficult. Let us consider equality constraints. And actually, even this case we have already covered in the lectures. How do we solve this problem? We still will need to make the gradient of something and set it equal to 0. It just will not be just the objective function, but we also have to consider the constraints. How can we include constraints into the cost function? Essentially, we have to remove them from the constraints and place them into the objective function. So what do we form? We form the Lagrangian. What is it a function of? X and, say, lambda. Okay, and we know that the Lagrangian is just the original cost function plus lambda transpose times the residuals of the constraint. So A equality times X minus B equality. Okay? Then we do what? We do the gradient both with respect to X as well as with respect to lambda. And we set both gradients equal to 0. So what's the gradient with respect to X? That's Px from the first term here, plus Q, plus, and we have X here. But it's at the end, so we have to transpose everything here, so that's A equality transpose times lambda. Here, it's just AEX minus BE. Okay? So now the unknowns that we are looking for are X and lambda. How can we solve for X and lambda? We have to write a system of equations where we separate the optimization variables. So the optimization variables are X and lambda. So we form a matrix here, and we set it equal to some constants. So the constant here is just Q, so we put it to the right-hand side. Here the constant is BE. So what we have here is we have P as the multiplier of X, and we have AE transposed as the multiplier of lambda. And here we have just the constraints, and here we have 0. We know that that 0 is in fact a 0 matrix. Okay? And now to solve for X and lambda, it just means to invert this matrix, call it capital M. Let's call this small m. So then X and lambda are M inverse times small m. Okay? So yet again, we are doing matrix inversion. So yet again, we have those limitations on the dimension of the system. Moreover, now we are doing an inversion of an even larger matrix. That means that it's also the number of equality constraints which contribute to the complexity of the algorithm. So when before the complexity was just in the order of n cubed, what will be now the complexity? What's the dimension of this matrix? Let's say that this BE here is such that we have small m constraints. What's the dimension of this matrix now? That's n plus m, and we are doing an inversion of that, so it's in general cubic function of this one. Okay? So now it's also the number of constraints which contributes to the solution. Now if I would ask you, what is the relation between n and m for the problem to be reasonable? And when asking about relations, I mean, what are the choices? Either n is larger than m, n is smaller than m, or n is equal to m. So what would happen if we have as many equality constraints as we have optimization variables? That's partly correct solution. So let's be more precise. Actually, it's not about this m here. Redundant constraint. So essentially what we should say here is that let m denote the rank, the row rank of equality constraints. So the number of linearly independent constraints. Okay? If we have as many linearly independent constraints as we have optimization variables, unique solution, nothing to optimize. Okay? What if we have less optimization variables than we have equality constraints? In other words, we have more equality constraints than variables, and all of them are linearly independent. Doesn't make sense. We don't have a solution because the system is overdetermined. Okay? So the only case where there is something to be optimized is where we have less constraints than we have variables. Okay? So usually this is still something like n cubed because m is smaller than n. So it's still primarily a function of the number of optimization variables. And to a smaller extent, it's also a function of the number of constraints. But the number of constraints is, well, to be reasonable, it's smaller than the number of optimization variables. Okay? So this is also something which we have covered in previous lectures. And this system of equations had a particular name. Do you remember that? It was named after those three important persons. That was the Karushkin-Tucker system of equations. Okay? So this we all covered. So let's move to the actual content. And that's how to solve quadratic programming problems when we have inequalities. And yet again, there was a general procedure to solve any optimization problems with inequality constraints. If you wouldn't know anything else, how would you solve quadratic programming problem? Using which method? Again, it has something to do with those three persons. So yeah, we would form the Lagrangian, but then what? Sorry? Brute force, but brute force doing what? What do you mean by evaluating lambdas?
Is that some of the lambdas to be active? So that
Okay. So what was the name of the method which was based on exploration of which constraints are active or not? Again, those three gentlemen. The Karushkin-Tucker method, or the Karushkin-Tucker conditions. Okay? And what we have said when we were covering this topic was the KKT method is a big, powerful hammer which can solve any optimization problem. Okay? The advantage here is that we are assuming that the original optimization problem is convex. Why is that an advantage in the KKT method? What was kind of the problem of applying or solving KKT conditions if we had a non-convex problem? So if we didn't know whether the solution is optimal or not, I mean, what did it mean about these conditions regarding whether they are sufficient or just necessary? So for non-convex problems, these KKT conditions are only necessary, meaning there might be a point which satisfies all conditions, but it is not the optimal point. However, if the problem is convex, and we are assuming that our problem is convex, then the first solution which satisfies all four Karushkin-Tucker conditions is the optimal solution. Now, what were the four KKT conditions? So what was, well, we have the Lagrangian, and actually it's the same as we had here. It's just that here we have ax minus b, right? So stationarity means the gradient of the Lagrangian with respect to the optimization variables must be equal to 0. So the gradient we already had, that was just px plus q plus A transpose times lambda is equal to 0, right? Then we had primal feasibility. What was primal feasibility? That were just the constraints. So AX less than B. And we should be more precise, and we should technically write a star here, because the gradient is 0 only at the optimum, nowhere else. Okay, so here we would put a star as well. Then we have dual feasibility. What was the condition? Those lambdas at the optimum must be larger than 0. And now comes the complementary slackness, this weird word. So, yeah, here. and each of them must be equal to 0. That means at the optimum, the i's optimal lambda times the i's constraint must be equal to 0. And we know that there are actually two situations when this could happen. Either lambda is 0 or the bracket is 0. If the bracket is 0, that means that the i's constraint is active. Okay? If lambda is 0, what can we say? Is the constraint active or not? There is a catch. So assume that lambda I is equal to 0. Does it say anything about activity of the corresponding constraint? Does it mean that if lambda is 0, does it mean that AIX is equal to BI, which means that the i's constraint is active? No. Because if you look here, if lambda is 0, then the bracket can be anything. So we cannot deduce this one. However, we can deduce that if the i's constraint is not active, meaning it is satisfied with strict inequality, then the corresponding lambda must be 0. Okay, so only this implication holds. The other direction does not hold. So we have stationarity, primal feasibility, dual feasibility, and complementary slackness. Now, how do we employ these kind of conditions to solve the quadratic programming problem? What would we need to do? What was the algorithm which has employed Karushkun-Tucker conditions to solve any optimization problem? So far, if the problem was unconstrained, or when we had only equality constraints, it was essentially just one iteration. Just do one matrix inversion and we are done. If we have inequality constraints, it is no longer just one single matrix inversion. It is not just a single kind of an iteration. Because what we need to do is we have to explore all possible combinations of active constraints. Okay? So if the inequality constraints would form a box, okay, and then we have a quadratic cost function, then we might have several situations. We might have that the optimum is here, so these are the level sets of the objective function. That's the optimal point. And it is contained in the strict interior of the constraints, meaning no constraints are active at the optimum. We might also have a situation like this, where the optimal solution is purely at this constraint. Or we might have a situation where the optimum is here, okay, where we have two constraints that are active. The problem is we don't know which constraints are active. Therefore, what we need to do is we have to try out all possibilities, stopping once for one combination of active constraints this KKT system is feasible. We can stop for the first kind of successful attempt because we know that our original problem is convex. So the Karushkun-Tucker conditions are sufficient and necessary for the existence of the optimal solution. But the point is, we would need to explore many combinations. How many combinations are there if we have 4 inequality constraints? So what we are saying is no constraints could be active. That's combination number 1 that we have to consider. Then each of these constraints separately can be active. So 1, 2, 3, and 4. Or 2 combinations could be active. So 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Okay? So we see that already for a relatively simple scenario, we have 5, 6, 8, 10, 11. Sorry?
Some of those combinations of 2 active constraints are
infeasible. I completely agree. If this is 1, 2, 3, and 4, 2 and 4, I mean, there is no point which lies simultaneously at 2 and 4. The problem is how do we detect that they are parallel, okay? In 2D, it's easy, you just draw. But usually these kind of optimization problems, you have hundreds of variables. So essentially we are in 100-dimensional space, which at least I have problems of even visualizing, okay? I can visualize 3D and that's where my kind of knowledge stops. Okay? So the point that even to decide that one of these combinations is infeasible, that's not easy. Actually, it is quite easy because we will simply find out that these equality constraints that we need to, or the system of linear equations that we will obtain when considering a particular active combinations. We simply find out that system of equations is infeasible. Okay? So we only find it out when exploring a particular combination. And let me say that, okay, let me renumber that. Let's say this is 4, this is 2, and let us consider this case here. Okay, that's the optimum. Essentially, we start by exploring an empty set, all single, all here. So it would be the very last active set that we would be considering. Okay? And we have also derived kind of the concrete number of active sets that we need to check. Essentially here it was something like the sum of n over I, where I goes from 0 to the number of constraints. That was the upper bound on the number of active set combinations that we would need to consider. For each of these, we would need to do one matrix inversion because we need to solve the system of linear equations. So the bottom line is the KKT method can be applied to solve problems like this. However, you should never apply the pure KKT method, which just tries out all possible combinations. You would be wasting your resources. Essentially, you would be doing something which can be done much easier than that. Okay? But in the worst case, even the most efficient algorithm still would need to go through all possible combinations of active constraints. So in the worst case, all algorithms are equal. In the worst case, they are bad, because this number explodes rapidly. We have seen it. Even for a case of, 100 variables and 10 constraints, then this number is 10 to the power of 100. Okay? And that's larger than the number of atoms in the universe. Okay? So even for small examples, all optimization algorithms can be very bad. Fortunately for us, in practice, the majority of practical problems that we want to solve admits a much faster way of obtaining the solution. And that's what we want to cover now. One of the methods to solve quadratic optimization problems is the so-called active set method. Essentially, the Karushkun-Tucker method is an active set method because we are exploring different combinations of active constraints. And actually, this active set method is kind of based on the feasible start Newton method, which we can apply to solve arbitrary optimization problems subject to equality constraints. So this slide here is just to remind us how the feasible start Newton method for equality constraint optimization problems has worked. It is a feasible start optimization method. That's why we are assuming that we have some initial point which satisfies constraints. Okay, so let's assume that X is feasible, and then we just perform a bunch of iterations. At each iteration, we have to determine the Newton step, which is the solution to this KKT system. Okay, so here we have the Hessian, so you can see some similarities here. We have the Hessian, we have A transpose, which multiplies the Lagrange multipliers, and here we have the gradient. And we have seen in the previous lectures how to derive actually this expression. We are essentially taking the Taylor approximation of the value function and then setting the derivative of the Taylor approximation equal to 0. Okay? Once we have the Newton step, we also need to determine the step length such that we can update the solution to some new value. So we are iteratively improving our solution. And if you remember, we have discussed something which said, what is the value of t which is required to reach the solution of a quadratic optimization problem in one iteration, what was the value? Well, we are talking about t, small t. We are not solving for t here. There is a value of t which gives us that this method, provided the objective function is quadratic and convex, this method converges in exactly one iteration for one particular value of t. And it was true if we had constraints, and it was also true when we didn't have any constraints. We said that the Newson method converges in exactly one iteration for quadratic optimization problems for a particular value of t. What was the step length that we had to consider? It was 1. Okay? So this is kind of the beginning of the active set method. It has nothing to do with the problem we want to solve a priori, because the problem we want to solve has inequality constraints here, but we will see in a second that internally to solve the problem with inequalities, we just have to solve a bunch of problems with equality constraints, where we would, again, similarly to the simplex method, we would have a clever heuristics which will tell us what the active set should be. So again, to avoid exploring all possible combinations, we will have a clever way which will tell us what are the best candidates for the active set to consider. That's what the active set method would be. But internally, it will be based on the feasible start Newson method applied to quadratic programming. So now the question is, how does this system here look like if we consider that the objective function is not some arbitrary function, but it is really a quadratic function? Again, assuming that P here is a positive definite matrix, meaning it's invertible. Okay? It's essentially what we have done here. Okay? So we have the Hessian here. The Hessian of the quadratic function is just P. Okay? The rest is the same as in the previous slide. And here we have the gradient of the objective function. And the gradient is clearly just Px plus Q. Okay? And we have to put the gradient to the right-hand side. Therefore, we have minus here. Okay? So this is how we would solve this optimization problem with equality constraints using the Newson method. First, we would, and here I would like to compare the whiteboard, what we have achieved. Actually, I've already wiped it, but it was there previously. We have seen that there was a similar system when we were just directly solving the quadratic optimization problem with constraints. And that version was that we essentially had to solve the, put the gradient of the Lagrangian equal to 0. So we had the equations Px plus A transpose lambda is equal to minus Q. And the second equation was just Ax is equal to B. Okay? So again, when we put it to a matrix form, it would be P A transpose A 0 times X lambda is equal to minus Q and B. That's how we can directly solve quadratic optimization problem with equality constraints. Notice that in the Newson method, we do it slightly differently. We do not optimize X. Instead, we optimize the increment. That's actually the difference that we have here. And there is also a difference in the right-hand side, which is a consequence of optimizing delta and not optimizing X directly. Just to kind of examine you. Why is there a 0 here, while here we have B? Is that a typo? Is that a mistake on the slide? Or is it really like that?
It's not delta.
Okay, so the constraint is that Ax plus delta is equal to B, right? Because we are optimizing over delta now. We are assuming that X is a feasible initial point. A feasible point has AX equal to B, right? So here we in fact have AX plus A delta is equal to B, but we know that AX is equal to B. Okay? So these terms just go away, so we have A delta is equal to 0. So that's why we have 0 on the slide and B here. Okay? Okay. So once we know how to apply the Newton method to solve quadratic problems with equality constraints, let us now take a look at how to solve a problem with inequality constraints. Since the procedure will be based on the feasible start Newton method, we are assuming that we have some feasible initial solution, and we will call X. We will also call by W the set of active constraints that we need to consider. Okay? Because the whole argument of the active set method is the following one. Imagine somebody would give you a problem like this, but you would not see it graphically. But the person would tell you that the solution is such that constraint number 1 is active in that solution. How would we solve the problem? Okay, so what we are saying is we have a problem where we minimize quadratic function subject to inequality constraints. Inequality, that's important. Now somebody tells you, I don't know where the solution is, but what I do know is that constraint number 1 is active at the solution. Simultaneously, by that we are saying no other constraints are active. So the set of active constraints here consists just of a single element, and that's 1. How do we find the solution then? If we know that constraint number 1 is active and the other ones are inactive, how can we reformulate this problem? It's just minimization of the same. Well, it still would be as many dimensional as here. Still x's are the... But here what we would say is that only the first constraint is active and the other ones are inactive. Okay? And suddenly we are back to the Newton method. Because the Newton method said if we have equality constraints, we can find a solution in a single iteration like this. Okay? Now, if somebody would tell you, no, it's not just constraint number 1 is active, but you know what? Constraints number 3 and 4 are active at the optimum, and no other constraints are active. How do we find the location of the optimal point? Well, the same, okay? So we minimize, and here we will have A3x is equal to B3, and A4x is equal to B4. Okay, and we are in the same situation as here. The only, yeah?
We still somehow need to know which constraints are active.
That's the whole point. That's the whole point. We don't know which constraint is active at the optimum. That's the whole message that I want to communicate. Like, what I want to say is, if somebody would be so kind to tell us which constraints are active, our task will be very easy. Do you agree with that? If you know the active constraints, it's just one matrix inversion and we are done. The only problem is we don't know which of these constraints are active. So now we have two options. Either we go in the brute force way and we try out all possible combinations. For each possible combination, we solve this problem using the Newton method, and we pick the point which is feasible. Clearly, if we pick constraints number 2 and 4, this system of equations would be inconsistent, so there would be no solution. So that's how we can rule out a particular combination. But in the worst case, we would need to go through all possible combinations. And it's similar to, if you remember what we said about the simplex method. A naive way how to solve a linear programming problem is to first enumerate all vertices and then just evaluate the cost function at each vertex. But we also said that enumerating all vertices is more difficult than finding the optimal solution. And the same here. the pure Karush-Kuhn-Tucker method would essentially mean enumerate all possible combinations. Now, enumerate them, meaning we have that sum of n over I, and this can be 10 to the power of 100, and enumerate means store it in the memory. And you don't have so much memory just to store all these combinations, not even to check whether they are feasible or optimal. Okay? So that's why the pure KKT method is not the way to go. And